Let's discuss the pancreas. It's a triangular gland behind the stomach. Here you can see, here's the stomach right there, and here's the gland here. And going to the next picture, I'm removing the stomach, and so now you can see the gland better, kind of surrounding the duodenum right here. So I go back, there's the stomach, behind the stomach. I'm removing the stomach, and then you can see the gland right there. The gland has a head, a body, and a tail we'll be talking about. Okay? It's a mixed gland. It has both exocrine and endocrine cells. The endocrine cells are located in something called the islets of Langerhans. The islets of Langerhans. And you have about 1 million of them. And they're just kind of spread out in here. So 99% of the pancreas is exocrine, traveling through a duct into this area of the duodenum with digestive enzymes. So the pancreas has digestive enzymes in digestion, but some of them intermixed within the pancreas are islets of Langerhans, which contain the endocrine cells, but 99% is exocrine. There are different kinds of, in each islet, there are different cells. You have alpha cells, beta cells, you even have delta, which you don't see here, and F cells. Okay? Alpha cells in the islets of Langerhans, the endocrine portion, secrete something called glucagon, we'll talk about. The beta cells secrete something that many of you know about called insulin. However, not many know that the beta cells also secrete another hormone called amylin. And amylin plays a role in glycemic regulation by slowing gastric emptying. So again, insulin lowers blood sugar. Amylin assists in that. Insulin, and we'll be talking about insulin, but amylin's role in lowering blood sugar is to slow the gastric, shall I say, the intestinal absorption. You don't absorb glucose from the stomach. The intestinal absorption of glucose, which would further cause a lowering of the blood sugar. Okay, let's go a little further here. So here's the pancreas. So the first hormone, so let me go further. All right, right here is a picture. Get this picture here. So, and this picture here, I want to show you. Here are those little clusters there would be the islets of Langerhans right there. The rest of the pancreas in this depiction would be the exocrine. So you can see these little islets separated out. You know what an island is? It's separated out just like this. So these would be the islets of Langerhans. Right here, this illustration is depicting the exocrine pancreas, because the exocrine pancreas would secrete digestive enzymes that would go into this duct. Remember, exocrine glands go through duct, exocrine, and into the duct and into the duodenum here, which would have been discussed in the digestive section. Here would show a nice blood supply here to the pancreas there. Okay? All right? So that's what we're looking at here that we discussed. Okay, this picture here then would be a blow up, a micrograph of the endocrine pancreas showing an islet of Langerhans with the various cells. The alpha cells producing glucagon, the beta cells producing insulin. Okay, and the rest of this would be the exocrine, as you see in this depiction here. So we go further. So here again is that same picture there. Right here, I'm going to the fact, again, this is a picture, a drawing of this. Here would be alpha cells right here. So the surrounding here, let's mind that the surrounding here would be the exocrine pancreas with their acinar areas. This right here would be the endocrine. This would be an islet of Langerhans endocrine portion separated by these structures here. See, these structures here are acinar cells, exocrine cells, that make the digestive enzymes. So this is a micrograph, actual micrograph of a histologic section, and this would be a drawing of that. So you can see alpha cells, beta cells, insulin, but I mentioned delta cells also. Delta cells secrete something called somatostatin, which is really a growth hormone inhibiting factor, and F cells secrete something called pancreatic polypeptide. But the two most notable cells are the alpha and the beta. Alpha, again, secrete glucagon, beta secrete insulin, but also that other substance I called amylin. Okay, so we'll go a little further. Okay, so now we're talking about glucagon. Its major target is the liver. So glucagon raises blood sugar, raises the glucose level. It does this by glycogenolysis. That means breaking down glycogen. Go back to your biochem section, chapter 2. Breaking down glycogen, because glycogen are long branch chains of covalently bonded glucose. So, and it's the storage form in animals. Glycogen is the storage form in animals. So when broken down from the polymer form to the monomer, then this would allow glucose to be released. Gluconeogenesis is the formation of glucose from other organic molecules, which would be amino acids and fats. Okay. And also it causes release of glucose to the blood because, like I said, it raises the blood sugar, the blood glucose level. Okay, let's go further. How does it work? It causes the liver to sequester, that means take in amino acids from the blood to make glucose, gluconeogenesis. Okay. The stimuli for its release are a fall in glucose level. Your blood sugar should be about 60 to 100 milligrams deciliter, so 60 to 100. That's kind of the normal. Sympathetic stimulation can also raise blood sugar. What would sympathetic? Fight and flight. You would need more energy. Rising amino acid level. This would stimulate glucagon to sequester amino acids, and then it could make it into glucose. Now that glucose, if these are rising too high, may even be used to make glycogen. Okay. Glucagon is inhibited by rising blood glucose because it's already high, insulin, which opposes this, and somatostatin, a growth hormone inhibiting action. So that's glucagon. That's glucagon. Okay. So we go further. All right. Now I'm going to insulin, which you heard a lot about. The effects of insulin are to lower blood glucose level, enhance membrane transport of glucose into fat and muscle cells, and we're going to talk about this particular part. Participate in neuronal development, so without adequate glucose in the developmental in utero of the person, they would not develop adequately, and even in the early stages of life after utero. It inhibits glycogenolysis, which basically means it's not allowing glycogen to be broken down, and it inhibits new glucose formation, all in an effort to lower the blood sugar. Okay, and again, it's being secreted by the beta cells along with amylin. Okay, let's go further. So right here enhances membrane transport of glucose into fat and muscle cells. So I want to go to this picture here, which you would have seen in my cell chapter, and I'm going to blow this up a little bit. What I want to bring out is that Glucose enters cells by something called facilitated transport. Study that in the cell. To have facilitated transport, you must have transporters, transmembrane integral proteins that would allow this water-soluble substance into the cell. Okay? Now, all the cells allow glucose in, but only one, shall I say, the GLUT4 receptor, the GLUT4 transmembrane integral protein and receptor need insulin. So only the GLUT4. So the entry of glucose into cells like the nerve cells and other things would not need it. The only cells that need insulin to allow glucose to enter the cell are skeletal muscle, cardiac muscle, and adipose cells, fat cells. Those are the only three. The other enters very easily. See, what would happen is, since skeletal muscle and fat comprise so much of the body, if these were allowed to have free access to glucose and just come in, they would sequester all the glucose. So everything else wouldn't have enough glucose and would cease to exist. So basically, by having a controller, which would be insulin on these, then would not allow free access for glucose to go into the cell unless there was insulin present in an adequate amount. Okay, so I wanted to point that out. Now I'm going to go to the next slide here. The way it works is this. Right here, what you have is secondary messenger aspect. Insulin is a protein. Insulin is a protein. It's about 51 amino acids, small protein. And what will happen, and actually, because it's less than 100 amino acids, many will call it a polypeptide. Remember, by good nomenclature, 101 and greater is called a protein, and less than 100 is called a polypeptide. So really, this would be really a polypeptide based upon good nomenclature, but some may call it a protein. But it's 51 amino acids, and what happens is, when it's made, it's actually secreted from the beta cell as a proinsulin. It's secreted as a larger molecule, and then it is cleaved. It's cleaved as it exits. It's cleaved into insulin. So actually, proinsulin is synthesized as proinsulin and then excised into a smaller one to come with the 51 amino acids. Now, once it travels, it will travel in the circulation because it's a hormone. And here are the receptors on cells. And what cells would they be? Cardiac muscle, skeletal muscle, and fat cells for this. So when it sits, now this goes back to endocrine again, because it can't get into the cell, it's going to use kind of a secondary messenger. So it's activating a transmembrane tyrosine kinase. Now, a kinase enzyme characteristically phosphorylates, energizes another protein. So by doing that, it turns on a cascade reaction, cascade leaves, and that cascade reaction causes transmembrane integral transport channels for glucose, which are stored inside this cell. Which cells? Cardiac, skeletal, okay, adipose. And then what will happen is, when this turned on, they're energized, vesicles will take them to the surface and they will pop into to here. So I'm going to stop here and I'm going to start right here next time to further